Hello everyone, my name is Shigeo Hakaku, and the title of my research is Comparative Study for Sampling-Based Simulation Costs of Noisy Quantum Circuits in collaboration with Keisuke Fujii. He is my supervisor, and we are both based in Osaka. In this talk, we'd like to show how to extend a particular memory-efficient classical simulator to noisy quantum circuits and perform a detailed comparative study of sampling-based simulators for noisy quantum circuits. Specifically, our results demonstrate how much noise makes quantum circuits simulatable and lead us how to design quantum circuits which have potentially quantum advantages. This is the outline of this talk. First, I'd like to explain the classical simulation algorithms for noisy quantum circuits. Second, I'll briefly review two sampling-based classical algorithms, stabilizer state sampling, proposed by R. Campbell and Mark Howard, and Heisenberg propagation, proposed by Patrick Rall and the others. Then, I'll explain how to extend the stabilizer state sampling algorithm to noisy quantum circuits we propose, and compare the cost of noisy random quantum circuits by both algorithms. Okay, let's get started. One of the goals in this era is demonstrating quantum advantages, which mean quantum computers perform an intractable task by classical computers. As you may know, Google demonstrated the sampling task with random quantum circuits. To verify the experiment, many classical simulations have been done, including full quantum state simulator, which computes all amplitudes, and tensor network-based simulators. However, these algorithms require exponential memory allocation owing to the number of qubits or the number of 2-qubit gates. Also, they don't take the noise on quantum computers into account for reducing computational costs. The noise deteriorates quantumness, so required memory for quantum simulations would decrease. By considering it, we would be able to simulate quantum circuits in a more memory efficient way. For a fair comparison between quantum computers and classical computers, we should take the best classical approach. To address this, we propose a memory-efficient sampling-based simulator for noisy quantum circuits. Each realization of the sampling-based algorithm I'll show requires polynomial memory allocation, and this algorithm takes the noise into account for reducing the costs. In addition, we compare the simulation algorithm with another one and find which algorithm outperforms the other. Also, we quantify the error rates of the noise which makes quantum circuits simulatable. Next, I'll briefly review the two sampling-based algorithms, the stabilizer state sampling and the Heisenberg propagation. The task of the stabilizer state sampling and Heisenberg propagation is to calculate the expectation value of an observable. For simplicity, we assume the observable is a Pauli operator. In the stabilizer state sampling, we consider the T-gate as an example. First, we convert the T-gate into the Clifford circuit with the preparation of the resource state, magic state, by the gate teleportation. Next, we decompose this resource state over stabilizer states and sample a stabilizer state with cause probability based on the coefficients of the decomposition. And finally, we perform the Gottesman-Neal theorem. By repeating the sampling step, we can obtain the expectation value. However, this algorithm cannot apply to noisy quantum circuits. In the Heisenberg propagation, as to the Heisenberg propagation, the observable evolves in the Heisenberg picture, but we sample a Pauli operator from the evolved observable. For example, we consider one quantum channel First, we evolve a Pauli operator in the Heisenberg picture, and then decompose the evolved operator over Pauli operators. Then we sample a Pauli operator with the quasi probability based on the coefficients. Finally, we calculate the trace of a Pauli operator in the initial state. Repeating these procedures, we can get the desired expectation value. Fortunately, this algorithm can apply to noisy quantum circuits. It is unclear which algorithm takes fewer simulation costs when we extend the stabilizer state sampling to noisy quantum circuits. So we address this question. I'll explain the sampling cost of both algorithms. In the stabilizer state sampling, the robustness of magic, ROM, determines the sampling cost. The ROM of a resource state is defined as the minimum of the one norm of the coefficients used for the decomposition of the resource state over stabilizer states. The squared ROM is proportional to the required samples. Also, ROM has a nice property. ROM is submultiplicative, so we can give an upper bound of a cost of a large circuit by the product of the cost of a small circuit. In the Heisenberg propagation, the channel stabilizer norm determines the sampling cost. The channel stabilizer norm of a quantum channel is defined as the one norm of the coefficients used in the decomposition of an operator. The squared channel norm is proportional to the required samples. Then I'd like to present how to take the noise into account in the stabilizer state sampling. We can move diagonal errors, such as the Z error, into a resource state by the gate teleportation. For instance, we consider the rotation gate about the Z-axis, followed by the dephasing noise, and find the resource state of this circuit. These are the definitions of the rotation gate and dephasing noise. When the circuit is error-free, the resource state is RZ theta plus. When the error occurs, the teleported circuit is like this. We can move this Z error backwards because it commutes with here. So the resource state is ZRZ theta plus. Therefore, the resource state of the rotation gate followed by the dephasing noise is given by this state. In this case, it is straightforward to take the noise effect into account by virtue of the dephasing noise. We cannot use this argument directly for an X or a Y error because they aren't diagonal with respect to the computational basis. To handle this, we propose a way to deal with non-diagonal errors through the gate teleportation of the Hadamard gate. For example, we consider the T gate followed by an X error. The teleported circuit corresponding to this circuit is here. We cannot move the X error backwards because the X error does not commute with here, but by rewriting X error as HZ8 like this, and insert the gate teleportation circuit of the Hadamard gate, the X error is taken as the Z operator on the second answer qubit. Similarly, we treat a Y error as the correlated Z operators on the two answer qubits. In general, a quantum circuit consists of Clifford and non-Clifford gates, both of which are subject to noise. We construct a method to merge the noise on Clifford gates into a neighboring non-Clifford gate as well. We consider quantum circuit consisting of arbitrary single and two-qubit gates followed by the single and two-qubit depolarizing noise respectively. We can confirm the unitary gate commute with the depolarizing noise as shown here. So we can merge the noise in Clifford gates into a neighboring non-Clifford gate to reduce the costs. Lastly, I'll compare the two simulation algorithms, the stabilizer state sampling and the Heisenberg propagation through noisy random quantum circuits. The scheme shows the random circuits we consider here. Single and 2-qubit gate are placed in turn, and single qubit gate are chosen by the set of gates, the root X, root Y, and T gate, uniformly at random. We assume 2-qubit gates are Clifford gates. Depolarizing noise occurs after each gate. The task we consider is to estimate the expectation value of a Pauli operator. We cannot calculate the simulation cost of the entire circuit because the computation of ROM or channel stabilizer known is exponentially hard for the size of the circuit. For this reason, our team exploits the patterns of the circuit. The entire circuit is reconstructed by the unit cell. We name the patterns of the unit cell according to the number of T gates, unit 1, unit 2, and unit 3. We can give upper bound of the simulation costs of the entire circuit combining the costs of units 1 to 3. As for the comparison of the two algorithms, we only have to compare the ROM with the channel stabilizer known because the required sample via each algorithm is almost the same as shown here. The difference is only using the ROM or the channel stabilizer node. As a result, we confirmed the stabilizer state sampling is faster when the error rate is low. This graph shows the scaling of the simulation cost as a function of the number of T gates in the circuit. 2 to the AT is an upper bound of the sampling cost, and the small t stands for the number of T gates. The x-axis refers to the error rate of depolarizing noise, and y-axis shows the A prefactor of the number of T gates in the sampling cost. When A is unity, the corresponding random circuit is hard to simulate. In contrast, A is equal to 0, the corresponding random circuit is easy to simulate. The optimized stabilizer refers to the stabilizer state sampling with two-fold copies of a resource state. Thanks to the submultiplicativity of the ROM, the sampling cost decreases by using multiple copies of a resource state. According to this graph, when the error rate is less or equal to 6%, the stabilizer state sampling is faster. Also, when the error rate is larger than or equal to 21%, we can efficiently simulate random circuits by the Heisenberg propagation. In summary, we'd like to propose a memory-efficient sampling-based simulator for noisy quantum circuits, and also to compare the two simulation algorithms, stabilizer state sampling and the Heisenberg propagation. We show how to simulate noisy quantum circuits by the stabilizer state sampling. We compare the simulation cost of noisy random quantum circuits by both algorithms and confirm the stabilizer state sampling is faster when the error rate is low. If you are interested, please look at our paper. Thank you for listening.